thank you so much. Okay, I would like to introduce Stefan Karpinski again. No introductions really necessary. Talking about Resolver. Should be very interesting.
All right, thank you. All right, my third talk of the day, so I'm happy to get the third one done. I'm Stefan Karpinski. I am the Chief Product Officer at JuliaHub. You know, check out our wares at JuliaHub.com. I'm talking about something mostly unrelated to work. It's called Resolver.jl. It's been a long-running project of mine. And it is a new SAT-based resolver for Julia package. You know, it's going to end up in the package manager eventually, but currently it's in a separate repo and hasn't been integrated. So just some background. What is package version resolution? What's the problem? Why is it interesting? The setup is there are packages. Each package has versions. Each version depends on a set of other packages. And there's some subset of pairs of versions of different packages that are incompatible with each other. And there's, you know, this is basically the same problem in most package ecosystems. Go has an interesting way of avoiding this problem being hard, but it seems not ideal in my opinion, but everybody else basically faces this problem. Actually, just briefly, the way Go avoids the issue is that they just don't allow things being incompatible. They just don't have a way to express that, and that does actually make this problem easy. A valid solution means that every dependency is satisfied. You know, you can't depend on something and you didn't pick a version of it. And there's no incompatible pairs of versions that you picked. So you need to pick, you know, a version of every package in such a way that this is satisfied. And it satisfies a set of requirements when there's a version for each required package. Okay, so the decision problem version of this, if you're in, you know, talking about complexity theory, is there a valid solution to this? And this problem of package version resolution is actually somewhat well known to be NP complete. This is a hard problem. And in particular, what it means that it's NP complete is that if you have a thing that solves this problem, you can solve SAT problems, which are also hard. So you might want to use a SAT solver, because if you don't, you're going to end up badly implementing a buggy, slow SAT solver, in effect. Of course, we don't just want any solution. We don't want to just know, is there a solution? That would be very useful. It's like, is there a solution to this? Yes, there is, but I won't tell you what it is. No, you want a solution, and in particular, you want an optimal solution in the sense that you want the latest and greatest of every package to the extent possible. Sometimes conflicts make it impossible to have the latest and greatest versions of two packages at the same time, but you'd like to do as well as you can. Yes, that was this slide. Okay, so, but it requires some notion of what makes one solution better than another. And we start by putting a preference ordering on the versions of each package. And the standard version preference order is that newer versions, bigger version numbers are better, right? We want the latest version of each thing. But sometimes you may actually want to do a different order for various reasons, and we'll get to that. Extending the order on versions to orders on solutions is actually a little subtler and more tricky than expected, but that is also something we'll get to. So what we do now, the current package.jl includes a version resolver. It uses a thing called belief propagation. It's heuristic. It does not always find solutions that exist, and if it finds one, it might not necessarily be optimal. But it works remarkably well. It's very good. And we've had it for like over a decade. And Carlo Baldassi implemented it, and occasionally, if you know, we put up the bat signal for Carlo if there's something wrong with the resolver, and he shows up and he will still fix things, even though I don't think he's doing any other Julia stuff these days. And we're very, very grateful for that, for the like decade of service maintaining this thing. Okay, so one of the big issues with the existing resolver is that the structure and meaning of version numbers is deeply baked into it. And that sounds fine, right? We're resolving versions. Why is that a problem? Well, the issue is that it bakes in this idea that higher version numbers are better. It also can't support pre-release versions, and it can't support build versions, so we have build numbers. So we have these like this horrible hacky ways to sort of work around that. But it'd be nice if we didn't have to do that. So why would newer not be better? One thing is you might want to fix versions. So you might want to be like, look, you know, for example, let's say you're adding a package. By default, what happens is that we add that as a requirement, and then we go through and re-resolve everything, and it changes everything. That used to be how it originally worked by default. That's kind of annoying, because you're like, look, I just added this thing. Why are you changing the version of every single thing that I'm using? Can you just leave them alone? Okay, so what we do right now is we go through and try fixing them. So we actually pin them and say, like, you're only allowed to use the version that's in this manifest. And then if that can't be resolved, I think we just give up and do the thing where we change everything. But it would be really nice if you could just say, hey, could you just prefer the current version, but otherwise, if you can't prefer the current version, like, feel free to, like, if you have to, go ahead and change it. Because then we wouldn't have to do this like pinning hack, and then, you know, if something can, like, you know, it's all or nothing right now. It's either like you pin everything, or then you're like, oh, you know what, we couldn't pin everything, we give up, we'll just change everything. It'd be nice if you could, you know, maybe, if it's necessary to change this one thing, just change that one thing and leave everything else alone. Another thing is you might want to avoid downloads, so you could prefer versions that you already have downloaded and installed, and that would avoid downloading new versions if you have one that you could use. There's also this concept of downgrade resolution. So instead of taking the latest and greatest of everything, take the oldest and shittiest of everything. And it's useful for testing lower compat bounds, like, because people have these upper compat bounds, and you kind of know those are right because you test them. But the lower compat bounds, are they right? Who knows? We don't know. We don't test them. Some people do test them. So Chris Rackauckas has been very good about testing lower compat bounds. And he had a hacked version of this, and he just changed it to use my script that uses this resolver code. So lower compat bounds don't sound very important. Like, why do we care? The reason you actually care about lower compat bounds being correct is because what will happen is everybody's tootling along and everything's fine until some incompatibility gets introduced in the ecosystem. And then what will happen is the resolver will say, oh, hey, I can't use these two new versions together, but here's this ancient version that claims to be compatible with everything. I'll just use that. And it doesn't work. It's a lie. It does not actually work with everything, but now the resolver will try to use it and everything breaks. So if the lower compat bounds are actually correct, then you can trust them, and you can, you know, if the resolver decides it can, you know, says it can use something, it actually will work. So that's why we care about those. Okay, so here's what we do now. This is the new approach. First of all, like, architect the thing to avoid coupling details of packages, versions, and registries. Resolver.jl doesn't know about these, even as types. Like, it doesn't mention them. It actually uses parametric types everywhere, and the type of package is just capital P, the type of version number is just capital V, and there's a couple other things that we need to have, but like, it truly knows nothing about these types. And the only requirement is, I think, packages have to be sortable, which we could probably eliminate that requirement, and then you're given an ordering on versions, so those don't even have to be sortable. We use an actual SAT solver. We're not gonna make that mistake. It's one called PicoSat, and it has some nice features it's very small, very compact, pretty fast, not state of the art, but good. And it has some nice features that are very useful. SAT solvers are very sensitive to problem size. So one of the key strategies here is do a bunch of pre-processing to make it so that the SAT problem that you construct is as small as possible. Don't just like make the biggest possible SAT problem you can and hope that the solver will not fall over, because it does if you make a big enough problem. All right. So some emergent features that kind of come out of this is, since it doesn't know about version numbers, you can give it an arbitrary preference ordering, because it's got no structure baked in. You just tell it, like, this is the order I prefer these things in. It generates optimal solutions based on a lexicographical ordering you give it of packages. It's like a priority order of the packages. And it gives you the lexicographically first optimal solution first, and then it can iterate more if you want more solutions for some reason, which you might want for compat bounds checking again. It has this semi-internal SAT problem API where you can basically say, look, for this resolver with these, with this registry, these registries and these requirements, give me a SAT problem. That API is generally useful. Like, you don't have to do resolution, you can do other things with it. Okay, so what is a SAT problem? It has a bunch of variables, and it has a number of clauses that reference those variables, and all of the clauses have to be satisfied. And in each clause is a disjunction of variables or negated variables. So obviously, if you have A and not A, and it's or, that's always satisfiable. That's a trivial clause. You could just delete it. It doesn't do anything. But you'll have an example here is like, A or not B or C, and then also that has to be satisfied, but also not A or B has to be satisfied. I didn't spend a lot of time thinking about this. I think this is satisfied by just like making C true, but maybe not. I'm not sure. I didn't think very hard about it, like I said. If you have a not and an or with something else, that's the same as implies. So in our encoding, we'll use that equivalence quite a lot. So this is equivalent to B implies A or C, and A implies B. Okay, so here's how we encode a package problem. We have the variables that we use are we have one variable per package, which indicates is this package installed. One variable for each version of each package, and the letters we use are P and Q and V and W. And here's some notation for properties. The packages that belong to a version, capital P of V. The versions of a package, capital V of P. So that's, those are kind of complementary. The dependencies of a version are D of V. So the dependencies belong to a version, not a package, because different versions can have different dependencies. The set of conflicts is just a set of pairs of versions. And then the conflicts of a version, sometimes it's convenient to talk about them as pairs, a set of pairs. Sometimes it's convenient to be like, the conflicts of V are these, and it's a set of other versions. Okay, so these are all of the clauses that we put in the SAT problem. The first one is set of clauses is a version implies its package. So if you selected some version of a package, that means the package is selected. And that's written as V implies P of V. A package implies some version of it. So if you've chosen a package to be installed, that means you had to choose one of the versions has to be chosen. So for all packages, the package implies, and this big V is an or, it's a n-ary or. So one of these versions has to be true. Could be, this encoding means multiple could be true, but right in the next one we say only one version of a package can be chosen. So for all packages, for all pairs of versions of that package, either not V or not W. So you can't have V and W both be true. So that says that you can only pick one version of a package at a time. There's situations where you actually want to relax that when you're using this as a tool for other stuff. Also, so a version implies its dependencies. So these are the interesting ones. The first three are kind of okay, yeah, normal setup stuff. This is a version implies its dependencies. So for all versions and all dependencies in Q in the set of dependencies of that version, the version implies the dependency. So if you pick that version, you have to install some version of its dependency. And conflicts are exclusive. So If V and W are a conflicting pair, they can't both be chosen. That's it. That's the whole encoding. What does this look like in code? So we loop over all the package names and we look up V underscore P, which is it's actually represented as an integer. The variables are just integer indices. And you look up the number of versions and then you generate clauses. And so the first set of clauses is that the version implies its package. So you iterate over all of the number of versions of the package, and then you do picosat add. And this notation here, negative integers are a negation of that variable, and positives are the positive of that variable. It's like a cute little encoding. It's all just, you pass integers to a C library. It's nice. So this clause is not P at version I or P. So that means P at version I implies P. That's what that says. And then you have to end the clause by passing it a 0. So the 0 variable says like this clause is over. So this is a clause that is always exactly two things. Here you have a clause with variable length. So the clause is not P. And then, oh, you know what? This is not negated. The negation here is wrong. So it's not P implies, and then you have a variable for every version of the package. So this will be, you'll have the P itself in there, and then you'll have like one variable for every version of the package, and then you end the entire clause. We do the same thing for exclusive. We do the same thing for dependencies. We do the same thing for conflicts or exclusive, and then that's it. That's the whole encoding. And so this part is like remarkably clean and simple. So again, preprocessing, SAT problems are sensitive to problem size. This is where the nastiness comes in. This code is just like horrific to read. It's very, very confusing and hard. So we use two strategies to minimize the size of the SAT problems. So one, we only include reachable packages and versions, and I will define what reachable means. And then we eliminate redundant versions that can't possibly be picked, and I will also explain what makes something redundant. So reachability, the concept is you start with the best versions of all your required packages. Those are reachable. You could consider installing them because it's the best version of a package that you need. You only consider the next version if all the better versions have some potential conflict, right? Like, we don't know if that conflict is gonna happen, but if there's no conflict, there's no reason to ever consider a worse version. So, for example, if a package just has no conflicts, why would you ever pick anything but the best version? There's no reason. So you don't have to even consider those versions. You also consider dependencies of any reachable version, right? Because so this thing, you consider this version is reachable. It depends on this other package. Okay, well now the best version of that is also reachable. All right. So in terms of this is an actual recursive definition of it, and the last one is quite subtle. So if P is in your requirements, then P1 is reachable. If PI is reachable and depends on Q, then Q1 is reachable. If PI is reachable and it has a reachable conflict, so that's like there is a reachable version that it has a conflict with, then PI plus 1 is reachable. And now this last one is a mouthful. If PI is reachable and it depends on Q, and Qn, which is the last version of n, is reachable and has a reachable conflict, then PI plus 1 is reachable. So what this is saying is that it's a very subtle, and this one took me a while to figure out. Like, it wasn't working, and I was like, why is this not working? Okay, you have PI, it doesn't have a conflict, but it depends on something, Q, and it's possible that we've been forced down to the very last version of Q, and that could also have a conflict. So now we could be in a situation where Q just isn't installable, but PI depends on it. Okay, well now we can't use PI because we can't satisfy its dependency. And so therefore we have to say okay, well, we might have to consider pi plus 1, which might have the same problem, but then we'll apply this logic and keep going down until we get to a version of p that doesn't have this problem. Okay, so this does pretty well. This like really cuts down on the number of versions of packages that you end up having to consider. And now there's this redundancy idea, and this cuts down even further on the versions that you have to consider. So suppose V and W are versions of the same package. Now, and you prefer V. It's a newer or better or whatever. It's whatever preference order you've chosen, V is better. And if the dependencies of V are a subset of the dependencies of W, and the conflicts of V are also a subset of the conflicts of W, there's never any reason that you would choose W over V, right? Because if you chose something that conflicted with W, either it also conflicts with V or it doesn't. Like this basically says like V is just strictly better than W in every way. So we can just forget about W. We'd never pick it. So this actually eliminates a lot of versions too. So now you go through and you filter these out and you just delete them from your data set. Okay, so you do those two things and you get a pared down SAT problem that is really like truly just the packages and versions you might actually have a good reason to consider installing. All right, so this is the overall process of constructing a SAT instance. Parse registry data for explicitly required packages, parse registry data for recursive dependencies of all the versions of those. You just kind of recurse until you've grabbed everything. I used to interleave this with reachability, but it was too gnarly, and then it turned out that like these first two steps are pretty quick and it's not that much data, it's fine. Like just load it all, and then once you've loaded the whole thing, do the reachability analysis and delete stuff. Then do the redundancy analysis and delete more stuff. And then you construct your SAT problem. Okay, so SAT solvers can find some solution or tell us that there is no solution, but how do we find an optimal solution? There are, a lot of systems seem to have gone for like stronger things like, modulo theories, solvers, and optimizers, and I was worried that I was gonna have to do that, and then I was like looking at Z3, and Z3 is big, first of all. It's going to be a big dependency to add to the package manager, and it's very complicated, and I was like, oh, this seems powerful, but like more than we need. So then I was happy that I figured out a way to optimize with just a SAT solver. So PicoSat has this cool feature where you can push and pop sets of clauses. So you build your basic problem, which the only thing it tests is this a viable solution? Like, not is it good, is it the best? It's just like, is there a solution that's viable? But then you can add more clauses onto that and then pop them off later if you don't want them anymore. So given a solution, you add a clause to improve some package version. You're like, okay, can I improve this package or not? And then at some point you get it, and the answer is no. That's no longer satisfiable. And then what you know is that the last version that you actually had a solution for of that package is optimal. That's the best you could do. And then you move on to the next package and you do the same thing. And when you've done that for all the packages, you have an optimal solution. Pretty straightforward. And yeah, then you're done. And you repeat this for each package. And once you find the best version, you lock it in, right? And then if you want to find multiple solutions, because there can be multiple Pareto optimal solutions. So when you find an optimal solution, then you look at that optimal solution and you add a clause forcing future solutions to not be strictly worse than it, basically. They have to be better in some way. There has to be like, why would I consider this if it's like this other solution I already found, but like worse. So basically there's some package where like there's a newer version than this other solution I already found. And then you stop when that's no longer satisfiable and you found all of the solutions. Or you've found enough solutions and you don't want to find more. Because there can be situations where there's like a lot of solutions. All right, so changing version preferences is now completely straightforward. The resolver doesn't care what order versions are in. You just give it an order, and when you're loading versions, and it does what it wants. So downgrade resolution, just reverse the normal order. Download avoidance, just look, sort the versions that you already have installed at the beginning, and that does it. Version fixing, look in the current manifest, put the version that's in the manifest at the beginning. And this can be done on a per package basis, so you can do things like, fix all the JLLs but try to upgrade everything else, or fix my direct dependencies but try to upgrade my indirect dependencies. You can change the priority ordering of packages, so the choice of like which package do I try to optimize first, you can configure that. You can be like, okay, well please try to optimize JSON before anything else. So the user can just pick this order. One thing that's kind of weird is that there's no sane way to prioritize indirect dependencies over direct ones. And that, it just has to do with the fact that if something is an indirect dependency, there's an ambiguity about whether is the newest version of that better or is no version of that better. And if you try to lock it in, it doesn't work. I've convinced myself that there's not a good way to do it. But then I kind of forget the details and come back to it, and I'm like, wait, surely there's a way to do this. And then I think more about it, and I'm like, no, there isn't. So, but I think this is okay. Like, do we care that much about prioritizing our indirect dependencies? I don't know why that would be that useful. So this is an open thing. Improved error feedback. We have all this powerful machinery. How do we give better errors when something isn't resolvable? Right now the errors are a lot of work has gone into this, but it's still very confusing when you get a not resolvable error. One possible approach that I'm thinking about is don't try to explain why it's impossible. I don't really care. What I care about is how do I fix it? So, and that's much more concrete and actionable. Like, what requirements could I remove that would make this work? Oh, I didn't actually need that, so okay, I'll delete it and now I don't have the problem anymore. Or, if you're a little more ambitious, what conflict could I eliminate? Can I go badger some developers to eliminate a compat bound with something, or release a new version of some things that are compatible? All right, that's it. I was gonna do a demo, but it's currently broken. I don't know how that happened. I'm not sure what the issue is, but it's broken. I'm wondering if I can show. Oh, yeah. There was a pull request. Where would I find that? Yeah, please ask some questions. Would I find that on Slack? Does anyone know? I mean, I can't just look for pull requests by Chris Rackauckus. That's like 12 million things. Julia Actions? No, I don't think so. You know what? I'm not going to try to find it. Let's just ask questions. All right.
Yeah, great work. The point you made about the resolver errors telling you what to do. One of the best uses of AI is taking a resolver error and putting it into ChatGPT and asking what I should do about it. Because it really does just say, 3 options are 1, remove this dependency if you don't need it. 2, do X or whatever. And short of taking the text output of the resolver and just, maybe PKG could hook in if you have an OpenAI API key, just chuck it out, get it back. Is this going to be able to make us write better English language advice?
I think we can, because one of the things it can do is it can give you a set of partial solutions. So and actually this is how the API currently works. It gives you, if it's solvable, it gives you full complete solutions. And if it's not solvable, it gives you partial solutions where the version is nothing for some of the things. And so I think, if there's 2 partial solutions and they each have 1 requirement missing, that's very easy to interpret. You're like, well, delete that dependency or delete that dependency, and you have a solution. And if you want to figure out what conflicts they could eliminate, you can basically like look at those two solutions and be like, okay, well, what would it take to merge these two? What things in here and here are conflicting? There's got to be some conflict, or you could merge them. And so that it could also be. So I think we can do it. I just haven't done it yet.
I have 2 questions. One is, how is Resolver.jl integrated with pkg.jl? Does that
Currently not at all.
Okay. Is it going to be like pluggable? Could we have other resolvers if we wanted?
I don't know that we like really want other resolvers, because I think this one just is the resolver. This just does it. And it's pretty hackable. If we want new features, I think we can put them in here. It's very straightforward. One nice thing, and I guess this I will show, is that the types are like completely parametric. This is kind of cool. So like the package info struct is parameterized on the package type and the version type. And it's just, versions is a vector of versions, and depends is a vector of packages, and interactions is a dict from packages to integers. The other part, you don't have to like pay it to like understand that, but it's just like nowhere do we mention it. So one of the nice things about that is that there's no logic in here that understands anything about registries or how the registry is laid out or anything like that. You basically, there's a kind of funky but like not that hard to use a callback API that lets you like show it how to do let me see if I can find the callback API. Oh yeah, here's the file. All right, so yeah, so this function, this file here uses the resolver API and the package APIs and kind of glues them together and does everything that's needed to get the resolver to know how to load packages. But it's not terribly long. Like it's a little bit gnarly, but this is it. Like this amount of logic is like strewn over thousands of lines of code in pkg.jl, whereas here it's just like it's all here, and nowhere else does it know anything about registries. So that's kind of nice.
My quick last question is, can I use this to fix the resolver issues with Python?
I mean, yes, it doesn't care about it being Julia stuff. You could like teach it how to read Python registry information. Do they even have registries? I don't know. But if you can come up with like the right data structure for Python, then it will give you answers. So, yeah.
I have a question about reachability analysis on, I think it was slide 24, with the dependency. It had to be all of the dependent versions had conflicts. Why does that not need to be Q1 when it says Qn is reachable with reachability conflict?
Oh, so basically, if PI is reachable, that means that everything higher than it had to have some sort of conflict, right? Like you wouldn't have gotten to QI. So you don't actually have to, you only care that PI is in the set, but if PI is in the set, then everything above like PI -1 is in there, PI -2, PI -3. I don't know if that was your question. Am I misunderstanding? Okay.
And we're unfortunately over time, and I would hate to cut you off because
no,
this is
that's
really
totally fine.
This is such great, useful stuff. Thanks so much, Stefan.
Thank you, everyone.